Our study organism is the Mexican axolotl Ambystoma mexicanum. These salamanders are endemic to the Xochimilco aquatic system in central Mexico near Mexico City. Axolotls are paedomorphic, meaning they never metamorphose into a terrestrial form, but rather grow and reach sexual maturity in their aquatic larval form. This species is listed as critically endangered by the IUCN, partially due to their high endemism and obligatory aquatic life history. Additionally, they face many external threats, including habitat loss and climate change. Mexico City has expanded throughout Mexico's central basin, and as of today, only 2 lakes remain that can support Ambystoma mexicanum populations, Lake Xochimilco and Lake Chalco. However, the axolotls have expanded their range by colonizing a man-made lake in Chapultepec Park. With rising temperatures due to climate change, it is unknown whether the axolotls will be able to adapt. Their extinction risk depends on their ability to withstand higher temperatures. As ectotherms, axolotls cannot regulate their body temperature via physiological processes. They instead must rely on other methods such as thermal acclimation and behavioral thermoregulation. Thermal acclimation refers to the ability of an organism to alter their physical state to tolerate undesirable temperatures, while behavioral thermoregulation occurs when an individual actively seeks out a certain microclimate. Axolotls use behavioral thermoregulation to achieve their thermal preference and optimize their metabolism and resource allocation and acquisition. Higher plasticity in this trait will confer adaptability to future climate changes. Thermal preference in axolotls has not yet been tested. In this experiment, we aimed to determine whether Ambystoma mexicanum were able to develop differing thermal preferences based on the temperatures they were acclimated at. With this information, we can better understand how they will be affected by the increasing temperatures associated with climate change.
A track was used to create a thermal temperature gradient in which the axolotl temperature preferences could be measured. The track was made of 2x4 wood that was screwed together and sealed with Flex Seal, a liquid rubber solvent which made crevices and cracks airtight and did not let water escape. The track was segmented into 3 sections of triangular pieces of wood that would fit into the middle gutter. These triangular pieces also acted as a barrier so the water could not pass through beneath the gutter. The track was separated into 4 sections, Section 1 having boiling water, Section 2 having no water, Section 3 being filled with ice, and Section 4 was where the axolotls were placed, and it was filled with water from that specific control temperature room. The purpose of having no water in Section 2 allowed for there to be no transfer of heat or cold from each respective side. Section 1 was filled with boiling water and maintained using an aquarium heater, whereas Section 3 was filled with salt and ice. Axolotls were selected randomly from a larger population available to be used. They were taken out of their control rooms 3 hours in advance prior to the experiment and placed inside a cooler that was filled with ice so we could lower their body temperatures below their thermal preference. We did this so that we can force them to thermoregulate once we put them in the track. Once the container that the specimens were in reached roughly around 8 degrees, then we were ready to use them in the experiment. Water from the axolotl specific control room was placed inside the gutter first, and then sections 1 and 3 were filled with either boiling water and ice, and we used aquarium heaters and bubblers to help maintain heat. Once the left side of the track reached roughly around 30 degrees and the right side reached roughly 10 degrees Celsius, and we had a temperature gradient in between in the track, then we were ready to start collecting data for the experiment. Once inside, the water temperature on the left side of the axolotls' bodies was recorded every 10 minutes for a length of 2 hours. Temperature was recorded with an AmpiProbe IR 750 with a thermocouple. This was repeated 6 times using 2 different tracks made of the same materials, totaling to 12 trials. The experiments were conducted identically at the same time. When doing new trials of axolotls from different temperature control rooms, the water from Section 4 was drained and the gutter was disinfected and refilled with water from the next room. We did this to prevent disease. Animal ID, track ID, time, and temperature were all recorded on the same data sheet.
After running the experiment, we compiled each individual's recordings into an average thermal preference, then calculated the mean temperature preference for each acclimation treatment. To interpret our results, we first compared the mean temperatures from each acclimation temperature. This least squares means plot visualizes our 3 data points. Individuals acclimated at 15 degrees Celsius had an average temperature of 19.97. Those acclimated at 18 degrees had an average temperature of 22.47, and those acclimated at 21 degrees had an average temperature of 22.46. We then ran an ANOVA to determine the significance of the variation between these means. As shown by the student's t-test, there was no significant differences between the means of any acclimation temperature. This is corroborated by our F statistic of 2.3609 and p-value of 0.1499. We had hypothesized that the acclimation temperature would correspond with the thermal preference for each axolotl. By acclimating individuals at lower temperatures, they would have a lower thermal preference, and those from the hottest temperatures would have a higher preference. Our data did not support this statistically, showing no significant differences amongst the three treatments. However, those acclimated at 15 degrees did display the lowest thermal preference by approximately 2 degrees Celsius when compared to the almost identical preferences of the other two treatments. This shows that it is possible for Ambystoma mexicanum to alter their thermal preference, depending on the temperature at which they are acclimated.
There were several sources of error throughout the experiment that could have contributed to the discrepancies in accuracy of the data collected. Maintaining a constant temperature on both sides of the track was difficult to keep. Whenever the hot side was given more boiling water, it would have resulted in warming the entire track, including the cold side. And this happened vice versa when we added ice to the cold side. The metal gutter was just way too good at transferring heat and cold temperatures. Since it was so difficult to maintain the temperatures, we were constantly losing heat and gaining heat on respective sides of the track. To combat this, we would replenish the boiling water and ice around every 30 minutes. However, this created a physical disturbance to the track and could have startled the axolotls during the trial and causing them to move away from their true preferred temperature zones. Lastly, there is a constant issue with having a vertical temperature gradient both inside and outside the metal gutter. In response to this, we added aquarium bubblers. However, they didn't stick to the track because the material of the suction cup and the material of the metal gutter didn't work so well together, and we had to push them down physically every 3 to 5 minutes, and this could have been another contribution to the noise / physical disturbance that we got from the ice, since we had to stick our hands in the track every so often just so that the bubblers could work. If temperature preference in axolotls can be a proven heritable trait, then captive species can be artificially selected for having higher preferences. Higher preference ranges can allow axolotls to thrive under new environmental conditions set by climate change. Captive species that are introduced to the wild can then interbreed of native species, both increasing population size and genetic diversity. Selecting for axolotls of higher temperature preferences can maximize species success in their native habitats. This can in turn ensure for survival of the species as well as increase their ability to be introduced to new environments, increasing their geographic ranges.
Due to our inconclusive results, we recommend that this experiment be replicated. In terms of experimental design, running each trial for longer than 2 hours may allow for better estimates of the axolotl's true thermal preference, as the starting measurements may be representative of the individual's stress rather than behavioral thermoregulation. The track could also be improved by minimizing heat gain and loss on either end, therefore allowing for a more stable thermal gradient to be established. Future studies would gain more valuable data by running experiments on more individuals from each acclimation temperature, reducing the effect of outliers. To build upon this study, we would recommend a common garden experiment, in which the axolotl's thermal preference is measured at one acclimation temperature, and those same individuals undergo acclimation to a different temperature and are reassessed for thermal preference. This would increase our understanding of not only whether axolotls can alter their thermal preference, but for how quickly they can and how wide the threshold of temperatures may be.
There are a few people who we would like to thank for giving us the opportunity to do this experiment and study the axolotls. First off, we would like to thank Barry for giving us the opportunity to study this and helping us out with the stats and the project throughout, as well as Regina for just always being there, a constant support and help mitigating all the tests that we need to get done and going through a lot of the trial error that we needed to go through in order for us to make this happen. And then for our team and with Sam and Bria and Olivia, who also contributed in helping create the track itself. And then to all the volunteers who fed all the axolotls that we got to experiment with. If you have any questions about our experiment, you can always email Jesse or I at our UCSC emails. But we would like to thank you for listening to our presentation, and I hope you enjoyed what we got out of this. Thank you.